Hello students, welcome. In our last videos, we have solved the potential delta function potential well problem. Now let us solve this when we replace this well with a barrier. So if we have now say a potential barrier here, delta function potential barrier, this is my Vx, and now Vx becomes alpha delta x. Now here no negative sign, so this become potential barrier, and now we can see easily that for potential barrier we don't have any bound state, so we need to only we are going to solve only for scattering state. So say this is my incoming flux and this is my outgoing flux, reflecting flux, and this is my say f e power iota kx transmitted flux. In this side there is a no further any flux moving towards minus x direction. So these are my flux, and we know now Schrödinger equation here v is 0, v is 0. So Schrödinger equations become minus h cut square 2m del 2 psi upon del x square, b is 0. So only we have equation, we have only e psi x, and we know the solution of this type of equations are given by, if I write this is del 2 psi upon del x square, and this is minus 2 me h cut square psi x, and this is equal to minus k square psi x, and the solution of this equation is psi x is equal to a e power kx plus b power iota kx. This is the reason x less than 0. Similarly, for x greater than 0, there is only transmitted flux. So my psi x will become only f e power iota kx. This is for x greater than 0 region. Now, in order to find the value of a and b, generally we write boundary conditions. And boundary condition is psi should be continuous. So psi should be continuous means I say this is psi 1, this is psi 2, or psi 1 or psi 2. So psi 1 0 is equal to psi 2 0 at x is equal to 0. So this becomes a plus b, and this becomes f. So this is the one boundary condition, and second boundary condition we are calculating at potential barrier at x equal to 0. So at x is equal to 0, you now have this is delta function, and we know discontinuity equation. We have seen in my last two videos. Discontinuity equations equation psi dash 0 minus psi 1 dash 0 is equal to 2m alpha upon h cut square psi 0, because at 0 both are same, so I'm writing psi 0, and here now there is a no minus sign. Okay, that is the difference between a well and here. Earlier here was a well and here sign was minus alpha. Now here sign is positive alpha, because this equation we generally get by integrating Schrödinger equation del 2 upon del psi square. We integrate this equation from minus e to plus e, uh, minus e2 plus e v psi x dx, and similarly e0 that becomes 0. And here now this is a minus, this is plus, this is the plus v psi x dx. Here vx is alpha, so this is come alpha alpha psi 0, it will go minus a, minus cancel. So this here, this term becomes a positive. Okay, that is the difference in our previous two cases. So now this is my equation, and now I can calculate psi 1 dash 0. Psi 1 dash 0 means this one, iota k a plus minus, this is minus here, minus iota k minus iota k b, that is iota k a minus b, and similarly psi 2 dash 0 means iota k f. Now if I solve this equation comes me iota k psi 2 0 f minus iota k a minus b, and this is, you have a 2 m alpha h cut square psi 0, psi 0. Okay, now if I solve this one, this gives me iota k, f is your a plus b, so a plus b minus a plus b cancels out. You have a 2 m alpha h cut square. Psi 0 is again a plus b. And now this equations become 2b, a cancels 2b, 2m alpha iota k h cut square, a plus b, 2 cancel. And if I am writing this as a beta, so this become b equals to minus iota beta a plus b, and from here b becomes minus iota beta a and 1 plus iota beta. This is the difference from previous case where it was iota beta and here was minus. So sign change, but the magnitude will not change. Okay. Sign is changing, but then the reflection and transmission coefficient magnitudes will not change in this case. So B you have. So once you have B, you can find now you have a plus B equal to F. So you can A plus B is minus iota beta A 1 plus iota beta equal to F. So this gives me, if I take A common here, so 1 minus 1 plus iota beta minus iota beta upon 1 plus iota beta cancels out. So F become 1 upon 1 plus iota beta A. This is a very important result. Questions are asked in examination on these things. So now if I find, so you see the beta here is a 1 plus iota beta. In the case of well, here we have a minus iota beta. So magnitude will remain same, but there will be change of phase when we have a potential barrier and potential well here. So now let us find a reflection coefficient. The reflection coefficient will be b upon a mod square. So b upon a mod, that means this will be beta square upon 1 plus beta square, and this we can write as a 1 plus 1 beta square, and beta we already know beta was what? Beta was your uh, alpha m upon k h cut square. So beta square will become alpha square m square k square h cut 4 and this is alpha square m square. This is your 2m e. K is your 2me upon h cut square, 2me upon h cut square. So this is remain h cut square here. So this is beta. I can write like this. So this become our reflection coefficient become 1 upon 1 plus 2me h. M also cancels. M cancels. So you have only 1 upon 1 plus 2e h cut square m alpha square. This is your reflection coefficient. Same like your potential well. Okay. And similarly, now you can find that your transmission coefficient T will be F by A mod square, that is 1 upon 1 plus beta square, and this is 1 upon 1 plus beta square. Beta square is your m alpha square, and 2e h cut square, 2e h cut square. So we see the magnitude wise both the cases are same. Either you take a potential barrier or potential well. Okay, only there is a change of phase. Okay, so we'll see some problem based on this two derivations. Thank you very much.